Okay, so we're doing an explanatory model to try to represent the proper structure for an unfolded protein. So currently, too many students visualize unfolded proteins as just simply stretched out polypeptide chains with no interactions with the aqueous solution surrounding it, with ions in the cell, with the ribosomes, with anything else. But in reality, an unfolded protein is not just simply a polypeptide chain in a vacuum. It's always constantly interacting with its surroundings. Even while on the ribosome and not fully translated yet, it begins folding. Folding is described as being a co-translational occurrence. And so this is what our model is going to try to address.
So our model has 4 different components. The orange balls represent different amino acids, and the string connecting all of them will represent the peptide bonds between those amino acids. And we have 2 different environmental factors. We have an aqueous environment, which is represented by the magnetic board on the right-hand side of the screen. And we also have the blue balls, which represent different intercellular components, representing different ions, carbohydrates, or any other thing that might actually affect how the amino acids interact. To actually use this model, there's 2 different ways you could actually do this. You can actually drop the polypeptide structure onto the magnetic board. That'll give you a different structure every single time. Or you could place it on the board and then shake the board to try to have the amino acids roll around on the board, showing different conformations. You can also change the different environments. So by moving the board, because it is flexible, you can actually move the board and change how the amino acids interact with the environment. You can also move around the different ions, or blue balls in this case, so different ions or carbohydrates or stuff in there interacting with the amino acids to actually change how the protein folds.
When the string of amino acids is dropped on the magnetic board, it can form unlimited conformations of states. The model on the left there shows the hydrophobic effect when the amino acids are exposed to an aqueous environment, like normal cellular conditions. The amino acids can form a compact structure to minimize exposure between the hydrophobic components of certain amino acids and the aqueous environment. And then models 2 and 3 in the middle and right side of the screen just show various interactions with the ions. Now to address some of the limitations of the model. Every good biochemist knows that most proteins are not 7 amino acids long, as indicated in our model. In actuality, most proteins are several hundred amino acids long, which increases the number of interactions that can form within the cell. Also, there's no way of representing protein quaternary structure. Quaternary structure is when multiple polypeptides interact with each other to form a larger globular protein, such as the case in hemoglobin. In our case, we only have 1 string of amino acids, so there's no way to show that. And then the third bullet point is once you drop the string of amino acids on the board, they're pretty much going to stick there until an outside force is applied. This is not it, so it looks like a pretty static environment, but this is not how a real cell is, because a real cell is fluid, and so the polypeptide would be constantly moving around. And then just functionally, the chain of wooden balls is on a pretty thin piece of sewing thread, so it can become tangled in between drops or while shaking the magnetic board. So occasionally it has to be taken off and untangled before another use.
Okay, so this is our magnetic board. We've got our ions here, and we're about to drop the polypeptide chain. And as we can see, the polypeptide chain interacts with the ion here. Looks like this R group must be more hydrophilic, and then the more hydrophobic ones are going inside, kind of showing us the hydrophobic effect. Okay, so here we have the board in a more flat conformation. We're going to see how this goes. Okay, so in this instance, this goes to conformation either 2 or 3, where we see it interacting with the ions, but it's not as compact as the hydrophobic effect, showing the different intermediate conformations that an unfolded protein can have. Now we're going to shake the board and see what happens and how that conformation changes. Oh, look, now because of the outside force, it's becoming a little more compact, a little more hydrophobic.